Thank you very much for the invitation. And the subject I'm going to talk about today is essentially the Archimedean components of automorphic representations in cohomology from the standpoint of Hodge theory. So in complex algebraic geometry, Hodge structures and more generally mixed Hodge structures are the linear algebraic objects that record the periods of integrals of differential forms on a variety. And Mumford-Tate groups, which I'll review at the beginning, are the reductive linear algebraic groups that describe the symmetries of these periods. And their orbits provide homogeneous classifying spaces for Hodge structures with given symmetries. And those are the domains, and they generalize period domains. And Philip and Mark Green and I have a book coming out on that, Princeton University Press, this month. So maybe tomorrow, I don't know, on the weekend. So there are two cases of Mumford-Tate groups and domains, or domains in particular. There's the classical case where the classifying spaces, these classifying spaces for Hodge structures, are holomorphically or anti-holomorphically fibered over Hermitian symmetric domains. And their arithmetic quotients, or at least their quotients by congruent subgroups, are Shimura varieties, or fibered holomorphically over Shimura varieties, and defined over a number field by work of Deligne, Milne, Borovoy, and others. Then there's the non-classical case, which is much less studied, where the quotients are in general not algebraic varieties at all. In particular, powers of the canonical bundle are going to have no sections, and there will be no sections of any homogeneous holomorphic line bundles at all in the case of a co-compact quotient. But they have a lot of higher cohomology, and that's going to be the subject of part 2. In either case, the coherent cohomology of the quotients can be computed by a Matsushima-style formula in terms of automorphic representations, so the decomposition of the automorphic forms into irreducible representations of the real points of the Q-algebraic groups here. And these are typically discrete series in their limits. And a result of Merkovich says that degenerate limits never contribute in the classical case. But this looks quite bad at first if you wanted to put a Q-bar structure or something and consider arithmetic properties of automorphic representations like totally degenerate limits of discrete series. And so you need a new idea. So what it turns out is that there's a lot of hidden arithmetic in Mumford-Tate domains and their quotients. On the surface, you already have a reflex field, just like for Shimura varieties. You have an adelic formulation. You have Hecke operators. All that stuff is there. Henri Carayol, in 3 papers in 1998, 2000, and 2005, discovered 3 ways to put Q-bar structures on the coherent cohomology of these non-classical Mumford-Tate domain quotients. He just did it in the case of SU21, and part of the point of the project that I've been doing with Mark Green and Philip Griffiths is to see how far it generalizes and to see if there is a more general formulation. And the first 2 here, which are Penrose transforms and cup products. So the idea is to use correspondences in cup products to relate cohomology of Shimura varieties to non-classical automorphic cohomology. And it seems to work in general if G is of Hermitian type. That's the Mumford-Tate group in this case. But otherwise, something more general is needed. And at least in the case of non-co-compact quotients, so that you have boundary components, there is an idea of taking Fourier coefficients of automorphic cohomology classes. And my second project, the project with Greg Perlstein, which is up there, was to see in general when the boundary components might be defined over Q bar so that you could formulate a notion of arithmeticity from that. So let me start by reviewing a little bit about Hodge structures and Mumford-Tate stuff. So we fix a Q vector space, some Hodge numbers, which are symmetric under reversing P and Q. And their sum has to be equal to the dimension of V. And then a Hodge structure is simply a circle homomorphism. It's a homomorphism of real algebraic groups, if you will, the real points of which are S1 and SLVR, with the property, so it only knows the parity of the weight of the Hodge structure that I want. But such that these prescribed numbers, HPQ, appear as the dimensions of certain eigenspaces of the circle homomorphism. Okay? So the z to the p minus qth eigenspace is VPQ. And I've fixed that p plus q always has to equal n. So this yields the more familiar notion of a Hodge structure, which is by a decomposition of the complexification of our Q vector space into PQ components with this property, and a descending, well, or equivalently, a descending Hodge filtration with a p opposed condition, which I haven't written, which is given by taking f dot to be all the VPQs with p greater than or equal to dot. And you write fi for the dimensions of those. The easiest example that's non-trivial is to look at the vector space generated by two rational generators and look at the decomposition where the v10 and v01 are generated by something of the form alpha plus tau beta, and that corresponds to the cohomology of an elliptic curve. Okay. Now, one usually works with polarized Hodge structures because otherwise you can't prove anything about them. And let's focus this a little better. So you take a symmetric or anti-symmetric according to the parity of n, non-degenerate bilinear form, and we say that phi is polarized by q. Phi is the homomorphism, or equivalently the Hodge structure, if and only if the first and second Hodge-Riemann bilinear relations hold. That is to say, the circle is contained in the isometries of the polarization, aught of VQ, and there is a positivity condition, where phi of I is something called the Weil operator. Then next, I introduce tensor spaces. TKL is v to the tensor k, tensor v dual to the tensor L. The Hodge tensors are special KL tensors. They are the ones that are rational and of type PP for some p. In other words, they are the things in here which are invariant under the circle. Okay, so Q is always a Hodge tensor of type 0, 2. Endomorphisms of V are tensors of type 1, 1, and Hodge tensors of type 1, 1 correspond to exactly the endomorphisms that respect the Hodge types. For this H1 of elliptic curve example with period ratio tau again, I'm not talking about the Hodge theorem. That gives obviously lots of Hodge structures from algebraic geometry. We have alpha wedge beta is a constant times omega wedge omega bar. That's type 1, 1. That's rational, and so you have something in Hodge 2, 0. Okay, so that gives something in there. Now, we might get an extra Hodge tensor sometimes. For instance, if tau is equal to I, we'll get an extra one in this way. And you get an extra Hodge tensor in general if and only if the period ratio is a quadratic irrationality and you have a CM elliptic curve. Okay, so the groups are going to encode this structure. They were invented by Mumford and generalized by Deligne to Hodge structures. We start with the polarized Hodge structure, and then the Mumford-Tate group of, I'll just call the Hodge structure by the name of the circle homomorphism, is equivalently either the biggest algebraic subgroup of the aught VQ, fixing all the Hodge tensors, or the smallest Q algebraic subgroup of aught VQ with real points containing phi of S1, so the Q closure of the image of the circle. It's a theorem that G is reductive and absolutely connected in the book of Deligne, Milnogus, and Xi. And then just a couple cases. For simple groups, it's true that a simple real Lie group G, curly G, arises as the real points of a Mumford-Tate group if and only if G has a compact maximal torus, which is equivalent to G admitting discrete series representations. In other words, having representations, irreducible representations in L2 of G of R that occur discretely in the spectrum. For tori, well, H1 of the elliptic curve has Mumford-Tate group equal to a 1 torus, a unitary group, if and only if tau is an imaginary quadratic number, and it's SL2 otherwise. There are no symmetries then. And a CM Hodge structure is more generally one with abelian Mumford-Tate group, and that generalizes the notion of a CM abelian variety, for example. So you can have CM Calabi-Yaus and CM anything else. Now the domains that we get by orbiting with these things, we start with a polarized Hodge structure with a Mumford-Tate group. It's essential that G be an actual Mumford-Tate group of a Hodge structure, and then take the connected real points. We're thinking of G of R as a real Lie group and orbit phi by it by conjugation. And that remains polarized by Q. And it's true that, in fact, if you take the entire locus of polarized Hodge structures by Q on V with Hodge numbers H and Mumford-Tate group G, then D is a full connected component of that. Secondly, it's also an open subset of the corresponding compact dual. So if you have G of R plus modulo H phi, then that is an open subset of G of C modulo a parabolic. So this is a compact. That's the isotropy group fixing phi. This is the thing fixing the corresponding Hodge filtration of phi. And this guy is always a projective variety over a number field. And that number field is the reflex field of the Mumford-Tate domain, if you will. So D is Hermitian symmetric. I will also say one more thing. It's always contained in a CM field, which is a nice fact. D is Hermitian symmetric, implies that H phi is maximal compact. So an example is CM Hajj structures. Those are zero-dimensional Mumford-Tate domains. Those are dense in every Mumford-Tate domain. Period domains are sort of, that's the smallest example of Mumford-Tate domains. These are the biggest ones. They're the ones that have G equal to the full automorphism group of Q. And a period domain DH, all the Hodge structures with this Hodge number and polarization Q, is a Hermitian symmetric domain if and only if H is one of these. So this corresponds to curves or abelian varieties, K3 surfaces, and God knows what. That's a pathological example, to be honest. But this says that DH, if you want something that is Hermitian symmetric, it's not the right place to look. You want to look at Hermitian symmetric Mumford-Tate domains inside non-Hermitian symmetric DHs. And that's one of the reasons why Mumford-Tates are valuable, because they give you all of these other Hermitian symmetric things. So we call D classical if it fibers holomorphically or anti-holomorphically over a Hermitian symmetric domain. And an example would be the period domain for Hodge structures of this type. This would be Hodge structures of weight 5. And they fiber holomorphically over Siegel's upper half space by bunching up these Hodge numbers and bunching up those Hodge numbers. This guy, in contrast, is non-classical. Okay? It doesn't fiber any, it fibers non-holomorphically over a Hermitian symmetric domain. Okay. Now, if I have a complex algebraic manifold, then I can assign a Hodge structure to each point of it in a smooth way. And you do that by taking a local system of rank equal to the sum of the Hodge numbers, a Q, a polarization of the local system, and a filtration of the local system by holomorphic subbundles. This formulation is preferred to the formulation with HPQs because those would vary non-holomorphically. These vary holomorphically. And you also demand that the fibers be polarized Hodge structures of type H and the flat connection nabla, annihilating the local system, satisfy this transversality condition. So now I fix a point on S, and I let V be the copy of the local system over that. So that's just a Q vector space now. I can get a monodromy representation from the fundamental group of S into the isometries of the polarization on V. And then the Mumford-Tate group of the generic Hodge structure in this family is always going to be a subgroup of Aut VQ. And you have a period map induced by the variation of Hodge structure given by looking at the variation of the Hodge flag or the Hodge decomposition into this quotient of the Mumford-Tate domain. So this is not just a period domain. This could be a more general Mumford-Tate domain. And this gives a locally liftable holomorphic and horizontal mapping. The horizontal part corresponds to this, and I'm not going to describe it precisely. If D is classical and gamma is a neat congruent subgroup, then D mod gamma is algebraic and fibers over a Shimura variety with compact fibers. If it's not neat, no torsion eigenvalues, right? D non-classical implies in general that D mod gamma is not algebraic. That's far from being proved, but you can prove it in, you can essentially prove it in the case where modulo is a small hanging nail in the case where you have a co-compact quotient. In particular, I state that there, you have no sections of non-trivial homogeneous holomorphic line bundles L, and so there are no holomorphic automorphic forms. And I can't resist mentioning the following example, which is due to Detweiler and Reiter from 2 years ago, really 6 years ago, but it was refereed for a long time. There exists a variation of Hodge structure from weight 6, H6, of a family of 6 folds with Mumford-Tate group G2 and Hodge numbers 1, 1, 1, 1, 1, 1, 1. So that's one example that shows Mumford-Tate, these exceptional Mumford-Tate domains are actually going to come in. Okay, simple Mumford-Tate domains. So henceforth, I'm going to take the following model. And it goes beyond just asking G of R to be semi-simple. I want, or really more simple in general, I'm going to take it, but it can be semi-simple for a lot of things I'm going to say. I'm going to take D to be G of R modulo not just any compact H, but modulo an actual torus, a maximal torus. So that very much limits the kinds of Mumford-Tate domains I can have. This is an example of something you could have. So this implies, in particular, that P is going to be a Borel subgroup, so I'll call it B from now on. So the D check is G of C mod B. And D check is then the flag variety of the Lie algebra of G. And so you take a Borel subalgebra and you're going to look at the orbit of it. And that is what D check is going to be. So the tangent space, thinking of this as the tangent space to D check, I'm going to break its tangent space into three parts. Into B and this stuff, n plus, which is supposed to correspond to the holomorphic tangent space. And I can further break this into the root spaces. So you think of n as the negative root spaces, and n plus as the positive root spaces, and h as the Cartan. Then you have a fact that open GR orbits in D check correspond to choices of phi plus or Weil chamber up to the action of WK. So I can sort of reverse what I've done here. Here I arrived at a choice of positive roots. I can go backwards as well. So just an example of how this works. I'm not going to actually reverse the correspondence, but the period domain for Hajj structures of type 1,1 is the upper half plane, and you have this positive root space and negative root space. That's the decomposition. The period domain for Hajj structures of type 1,1,1,1 of weight 3, which I'll call DI, D1, corresponding to this Weil chamber here. I'll use interchangeably because I'm going to use this example a lot in this talk. This is the diagram for SP4. And you have 4 Weil chambers which are not equivalent under the action of the compact Weil group, which is just the flip that takes the greens into each other. Those are the compact roots. And so here are my positive roots for this D1. Inside of that, I have the subspace corresponding to my compact root, and that's a P1. And so that's a very typical situation. What's going to happen is you're going to fiber non-holomorphically over Hermitian symmetric domain, the Siegel upper half space, with compact fibers P1. That's the way this looks. But it's a non-holomorphic fibration. Points phi of D1 can be represented geometrically by indefinite Lagrange flags. Lagrange means that Q of this line against itself is 0, where this is the projectivized third Hodge filtran. This is the projectivized second Hodge filtran, namely the line in PV. This solid locus that I've drawn is the positivity condition. So this line has to go through it, but this point can't be on it. So, oh, yeah, and the domain corresponding to the holomorphic chamber here, that's DH, which is this thing I already introduced, and that corresponds to definite Lagrange flags, which are entirely contained inside that hyperquadric. Now let me come to Carayol's example. I'm not going to use this so much, but this is a true Mumford-Tate domain. So we let V be a 6-dimensional Q vector space, an alternating non-degenerate polarization, and now an action, an embedding of an imaginary quadratic field into the endomorphisms of this Q vector space. And that decomposes Vf into V plus and V minus into 2 eigenspaces, and we assume that V plus is Q isotropic. Next, I'm going to consider Q-polarized Hodge structures phi with Hodge numbers 1, 2, 2, 1, such that the V plus intersects the Hodge spaces in this way with this dimension and the V minus with these dimensions. And so that, of course, the embedding of the imaginary quadratic field respects the Hodge decomposition. So then we can introduce an F Hermitian form, and that has signature 2, 1. And you can then observe that the Mumford-Tate group is in fact this. The symmetries of the polarization intersect the Weil restriction of GLV plus. And so the real points are just an indefinite unitary group, and the orbit is going to geometrically look like this. You look at the Hodge filtration restricted to V plus, and you look at the 3,0 part and the F2 part. So the F2 part gives a line in PV plus, and the F3 part gives a point in V plus. And so there's a correspondence between points phi and flags with the point not in the ball and the line passing through the ball. And it corresponds to this chamber that contains the compact root and this choice of positive roots. So one more example. We take V 7-dimensional, Q symmetric, and of signature 3, 4. Then there exists a Hodge tensor, a 3 tensor, such that the isometries of the polarization and the tensor are equal to G2. So G2 is being contained in SO34. That's what this is saying. And then the possible gap-free sequences of Hodge numbers of a Q-polarized Hodge structure on V with Mumford-Tate group G2, and this is proved in our Mumford-Tate group's book, are these three things. And this one is the only one that's going to produce one of the form that I want, G2 modulo a torus. OK. So now let me say something about cohomology and line bundles.
What is the reason you want it to be a torus?
It's easier to, you get line bundles. Much easier to deal with as the homogeneous things that you want to deal with. It's complicated enough. So, I mean, if you would just get more general, you would have to look at representations of H more generally. OK? So here the representations are just characters. The setting is the same. I have the roots inside the weights, and I assume that half the sum of the positive roots is in the weight lattice. And then to each weight, I'm going to associate a homogeneous holomorphic line bundle, L mu. So mu is the weight. And I look at the stuff, which is GR cross C modulo this equivalence, if you will, just the fiber product over H down to D. So this gives a line bundle over D, and it in fact extends to D check. So D check is G of C modulo the Borel. And so the tangent space, as I already observed, is N plus, this nilpotent sub-Lie algebra. And because the canonical bundle restricted to, well, at the point, the reference flag, is going to be the highest wedge power of n plus check, since the wedge D of n plus check has weights equal to the sum of the negative roots, you get L minus 2 rho isomorphic to KD. So that's the canonical bundle. So for G equals SL2, the upper half plane, you can, I mean, it should be familiar that this is the modular forms of weight K. So that's the gamma invariance in the cohomology. For G naught a product of SL2s, by contrast, H naught of D with coefficients in O of L minus K rho for K positive is 0. That's because there's going to be some compact sub inside the domain to which this will restrict to a negative line bundle and die. Sections won't exist. So next, we have L2 and Dolbeau cohomology. Mainly the Dolbeau cohomology is what I'm interested in, but you can state a nice result about the L2. So the discrete series are indexed by the regular weights, not on the walls of any Weil chamber, modulo the action of the compact Weil group. And Schmidt's theorem says that you can basically get all of them with the L2 cohomology of these Mumford-Tate domains. So this is the coherent cohomology. And you have to add half the sum of the positive roots to get the corresponding discrete series representation. And here I'm thinking of this as a representation of G of R by left translation. That will be important later because there will be something where it's not left translation. So the point is this vanishes in every degree but 1. And this has to do with the curvature of D. And so we get 0 unless P is equal to Q of mu minus rho, where Q is defined to be, this is the positive compact roots and the positive non-compact roots, and you have to be negative with respect to a certain number of those and positive with respect to a certain number of those. OK. So the discrete series representations for SL2 are gotten by looking at sections of, this is the K over 2 tensor power of the canonical line bundle. And a picture of dk minus 1 is this. You have some one-dimensional space in weight minus k for the torus. And then all the weights are k minus k minus 2, minus k minus 4, and so on. And you have the action of the two nilpotent Lie algebra generators going back and forth. And if you go off the top, you go to 0. But it goes infinitely in that direction. And to make this concrete, you can set up something that looks an awful lot like the standard inner product on modular forms, except these aren't modular forms. And then you set up a representation into automorphisms of these L2 functions on the upper half plane, which again looks like a lot like the standard modular form transition condition. And then dropping the L2 condition and looking at just H naught of this replaces this nice unitary discrete series representation by a so-called maximal globalization, which is a big Fréchet space. And more generally, that's the stuff that we're going to be looking at. I won't care about the topology on it, though. It's just, it gives a continuous representation. That's all one needs to know. So the big theorem of Schmidt, then, is that HP of dO of L mu is always the maximal globalization of its underlying Hajj-Chandra module, and that is precisely this L2 cohomology when mu plus rho is regular anti-dominant. There's another case that's important where P is equal to Q of mu plus rho equals 0, and D is classical. So that's sort of a holomorphic discrete series case. And in both cases, the embedding of L2 cohomology into Dolbeau cohomology is dense, and if you go beyond the dimension of the maximal compact guy, the Dolbeau cohomology is 0. So we can use a nice little technique to get the full K-type. Since we know that these give the discrete series representations, we can figure out what the discrete series representations, weights, and K sub-representations look like in this way. We simply remember that the normal bundle of this maximal compact subvariety in D is equal to the fiber product over H of the maximal compact subgroup with P plus. So here K is the compact part and this is the non-compact part. So if mu plus rho is regular anti-dominant and we make this assumption on the root spaces, then Borel-Weber-Bott gives us a vanishing condition which allows us to extract short exact sequences from the long exact sequence of sheaves associated to the ideal sheaf of Z twisted by L mu goes to the trivial sheaf twisted by L mu goes to the skyscraper sheaf on Z with coefficients in the restriction of L mu to Z. And so what this does is this says if you want to know what this is, it's going to be this plus whatever this breaks into. This is going to be then this, which is this plus whatever that breaks into, and so on and so forth. And eventually, you get a decomposition of this as into, of the K finite vectors inside this into irreducible K representations. And it looks like this, and this is something that is readily computable, again, by using the correspondence between this and P plus check. So in the classical case, you can do something similar. And I won't go through the details here. And either way, we'll give you back the SL2 example, and you can actually get back the full action of the Lie algebra G as well by using these standard maps. OK. So what does this give for G equals SP4? So we identify K equals U of 2 irreducible representations by their pullback to U of 1 cross SU2. That's just because I'm dumb. I'm doing it naively. So Sj of I is what I'm going to call the J standard irreducible representation of SU2 twisted by character of weight I over 2 times alpha 1 plus alpha 2. Now what are these? Alpha 1 is half this vector, and alpha 2 is half this vector. So this vector is alpha 1 plus alpha 2, and so on. These are the roots of SP4. And these are the ones that I said were positive for my choice of Weil chamber there. But now I'm going to choose a different one. I'm going to choose DH. So for DH with coefficients in O of L lambda K by the holomorphic discrete series, case 2 over there, is going to be this discrete series here, where rho H is this half the sum of the positive roots in that direction. And lambda K henceforth is going to denote this this weight here. So this will be a standard discrete series representation I'll use from now on, and it looks like this. These are the irreducible k-reps, okay? And you can see that there's a new one appearing here. Like this is actually, this has rank 2 in this dot, and this has rank 2 in each of these dots, and in this dot that I didn't draw it would have rank 3. So sort of new sub k-reps appear as you go higher and higher. So this is the decomposition, what it looks like. Here's another example of something you can get with the holomorphic chamber and the holomorphic Mumford-Tate domain. So you get these nice k decompositions. But you can also get the totally degenerate limits of discrete series as an example of the limits you can get. So limits of discrete series are these tempered representations parameterized by pairs, lambda and c, where lambda is in C, but lambda can't be orthogonal to a C-simple compact root. Okay? So if I go back to the picture up here, then you can't, if you want to have that your parameter is 0, then it's going to be orthogonal to any C-simple compact root with respect to your given C. So you have to choose a chamber that does not have a C-simple compact root. That would be the two non-holomorphic chambers. Okay? So for SP4, these are the two totally degenerate limits, which I'll call TDLDS from now on. And there is, well, we've been talking with Schmidt, and Schmidt has communicated to us that a theorem of his extends to the limit, and so you can use this H1 of di with coefficients in O minus, of L minus rho to compute this TDLDS. And when you do that, you get a big mess if you try to draw it this way. But if you just draw the highest k types, okay, so here that would be equivalent to drawing just the stuff below this line. Here it would be just drawing a few of the dots. Then you cover this entire set of 3 chambers in here. And I've drawn just the lowest k type because I'll need to use it later. Okay? Now, what does this say about cohomology of the quotients? So if we assume gamma is co-compact, which I will more or less henceforth, then you have a nice theorem from a long time ago in a paper of Griffiths and Schmidt, which says that if p is not equal to this q of mu, then you don't get anything. But if p is equal to q of mu and k is sufficiently large, then the cohomology of this line bundle of the kth powers grows at the order of k to the dimension of the Mumford-Tate domain. But we would like to actually compute these things. We would like to have a representation theoretic interpretation of this growth, for example. So you introduce automorphic forms, which are the k and zg finite C infinity functions on the quotient g of r mod gamma, and you have a decomposition over the unitary dual of g of r into irreducible representations, and m pi gammas are the multiplicities. So this may include more than discrete series, because although the spectrum, yeah, because although the spectrum is entirely discrete, you don't know. That doesn't mean you just get discrete series. Yeah.
Some of us live with the rest.
Right. Yes. It's a very important fact for many careers. So HP of D mod gamma with coefficients in O of L mu we can compute by this nice Dolbeau complex. And the Dolbeau complex itself can be readily computed. So I'm going to replace this L of mu by twisting by C of mu and look at the H invariance. And that corresponds to, instead of looking at forms, I can look now at C infinity functions and just identify these wedges of the Lie algebra with left invariant differential forms. And then I have homomorphisms from that into here. So the weights of whatever I choose here and whatever I have here have to be the same for this to be a hom over H. So now this mu comes outside as a minus mu, and I'm taking cohomology of the C infinity functions on g of r mod gamma. in a certain weight. And now the C infinity of G of R mod gamma, because gamma is co-compact, decomposes into V plus, well, as it did above, and I just used that here. And moreover, this becomes a finite direct sum from an infinite direct sum by a theorem of Castleman and Osborne, which says that the infinitesimal character of any representation contributing to this has to be minus mu plus rho, chi minus mu plus rho. Now, if we assume mu plus rho furthermore is regular, and the corresponding discrete series representation is integrable, then this can be relaxed. The condition of integrability can be relaxed somewhat, and there's a property due to Williams that allows you to do that. But then you get that, in fact, this space is one-dimensional, and it's the only one that's non-zero in the direct sum. Okay, it's just the discrete series that contributes. But we're interested in cases where that doesn't happen. So if mu plus rho equals 0, then you can show that for SL2, SP4, and SU21, only TD-LDSs contribute. There's a confusing terminology issue here. For SL2, you have no degenerate limits of discrete series, but you still have a totally degenerate limit of discrete series.
Totally degenerate, that's what that means.
It means that the infinitesimal parameter, it means that it's 0, right? Right? The Hajj-Structure parameter is 0. So this is the first generalized Carayol, if you will. I'm going to introduce some correspondences between holomorphic, well, classical and non-classical Mumford-Tate domains. So we know that there is a domain for each Weyl chamber, if you will. And the way I do this is I fix a Borel subgroup, and then I take a conjugate by something in the Weyl group, and then I identify this as an open subset of the action of G of C on the Borel subgroup by conjugation, which identifies with G of C modulo the Borel. And so this is how you get these open orbits. Now, if I take the intersection of all of the open orbits of BWs, then I go modulo HC. Let's see. I think I wanted to take G of C acting. No. This is a product. Sorry for the confusion. This is a product. All the elements in here times all the elements in here. That's what this is supposed to mean. So I'm taking the intersection over all W and W of that, modulo HC. That is an open subset in G of C modulo HC, which I'll call the compact dual of W. And now, for each W in the Weyl modulo the compact Weyl group, we have a holomorphic projection that goes from W to DW, and that's compatible with W check to D check. And the CM points P and W will be defined to be those that project to CM points in every Mumford-Tate domain. So an example here for the SP4, I can take W, I can realize it in a variety of ways. I can realize it as an open subset of D1 cross D1, or I can realize it as the set of Lagrange quadrilaterals with these all Lagrangians, and in this configuration relative to the hyperquadric, and with P1, P2 perpendicular to P3, P4. And then I have the projections to the various domains that isolate one of the lines and one of the points in it. And this gives a 5-dimensional, these numbers denote the dimensions of these things, gives a 5-dimensional correspondence sitting between over D1 and dA. And dA is the guy that fibers holomorphically over the Siegel upper half space. So now, what does this have to do with automorphic cohomology? This is where this Eastwood, Gindik, and Wang formalism comes in. So the fact is that W is Stein, and the fibers of the projection are contractible. And with that known, you can apply the hypercohomology spectral sequence to get that this spectral sequence computes the cohomology of W with coefficients in pi inverse of O of L mu. And then applying the Leray spectral sequence, I get that the same thing is going to be computed by this different spectral sequence. And then when you use the fact that W is Stein, you find that A has to be 0 in this. And when you use the fact that the fibers are connected, you see that Q has to be 0 in this. And so this gives you that the cohomology of the complex of H naught of W, sections over W of omega dot pi, the relative de Rham forms with coefficients in pi upper star of L mu, has to compute HP of this thing we don't care about anymore, and that computes HP of D with coefficients in O of L mu. And the same argument goes through for your arithmetic, whatever kind of quotients you want. And we can't use J to do this because it's not Stein. It would be more convenient, but it doesn't work. So now, this allows us to get correspondences between maps between cohomology, so Penrose transforms. So what do? I'm going to cut through some of this. But the idea is that you are going to take, well, first we need a standard form. So how are we going to get our standard form? The form is going to lie in the relative cohomology of the projection from J to D. And it comes from one of these Mara-Cartan forms, one of these left invariant forms in G inverse DG. Now, given something in the 0th cohomology of D prime, the holomorphic guy, if I take pi bar upper star of F in here, that should be pi bar prime upper star of F omega, and that goes into J, then what you do is you use omega, and the fact that omega is in omega 1 pi bar, you're going to multiply that with pi upper star of F and get a section of omega 1 pi bar upper star L mu. Okay? The way this works is I'm using the fact that for, where is it? Mu plus rho is equal to mu prime plus rho prime. Omega essentially trivializes this bundle over J. Okay, so there's an equivalence of bundles here. And then what I do is I observe that if my pullback of this form to W is a d bar coboundary, is a d pi coboundary, a relative coboundary, then pi bar upper star of F times omega is equal to d pi bar of G. In other words, it's going to be a coboundary for this relative, those relative de Rham forms. But then you use the fact that J is covered with compact P1s, well, with P1s, and G restricted to any of those, if it was the pullback of a section of this form, would actually be a section of a negative line bundle and therefore 0. And this is under the following assumption, that mu is negative against the positive compact root alpha 1 minus alpha 2. So when we make that assumption, we're OK. And that assumption holds when we're dealing with sections that correspond to Ziegel-modular forms, as I'll get to in a second. So all told, what we get is a map from H naught of coherent cohomology of D prime to something which is equivalent to H1 of D, coherent cohomology of D, with coefficients in a slightly different a line bundle corresponding to a slightly twisted weight. So Penrosette is evil infinitesimal twin. So, and they're not really essential on this slide. The point of this slide is to get to prove that this guy is an isomorphism for certain weights. So the way we do this is we observe that on the compact fibers of D going to H2, this is the non-holomorphic projection, L mu restricted to Z being a section of a negative line bundle, being a negative line bundle implies that the H naught will be 0. And so the Cartan-Loray spectral sequence allows us to equate the gamma invariance in cohomology and the automorphic cohomology. And this gives the top row of this map now. Okay? So that allows me to descend this modulo gamma. Okay? We proved this was injective already, so it remains injective under descent modulo gamma. Now what I do is, assuming property W, I get that this is computed by Lie algebra cohomology, and this is computed by Lie algebra cohomology, and you're using the same representation, so you have the same multiplicities, and this is one-dimensional and this is one-dimensional, and so these are both M of gamma dimensional. And so you get right away that it's an isomorphism. Now you can also complete the diagram by tensoring with something in the dual nilpotent Lie algebra. And that's what I call the Penrosette transform. So that's the thing that corresponds on the level of Lie algebra cohomology to the Penrose transforms there. And so you get that P gamma, for instance, is an isomorphism from scalar automorphy factors, Ziegel-modular forms, to H1 automorphic cohomology of the non-classical guy. And you also get an isomorphism, for instance, between vector-valued Siegel modular forms. These are two vector-valued Siegel modular forms in 2H2 in a slightly different weight. So why is this interesting for arithmetic stuff? Well, you have classically three ways of describing arithmeticity on, say, Shimura varieties. You can talk about the canonical model. You have sections of some algebraic de Rham Hodge bundles that correspond to your H0 sections, or your modular forms here, equivalently. Or you can look at values of automorphic forms at CM points, or you can look at eigenfunctions for the Hecke operators. For non-classical automorphic cohomology, you still have all these three things available. That's the interesting fact. 3 is available directly by an adelic description, though we haven't computed anything yet. 1 is available via the Penrose transform for G of Hermitian type. So here you can say, what are my Q-bar automorphic cohomology classes? Well, those are just going to be P gamma of my modular forms. And it's very important here that you have not just a surjection, but an isomorphism, because otherwise you would have to worry about co-boundaries being defined over Q-bar. And then 2 is available from this Penrose transform stuff as well, in a sense, at least from the Eastwood-Deacon-Wong stuff. From the fact that these vector bundles, in fact, everything is defined on these compact duals, we get an arithmetic structure on these twisted relative de Rham bundles. And there are restrictions to CM points because the CM points are arithmetic under the definition over Q bar of the Mumford-Tate domain's compact dual and the compact dual of the correspondence space. So I'm using the idea, like the definition of Q barness that comes on the periods side. All right? I'm not using the definition for going modulo gamma and embedding in projective space or something like that. So this is not the canonical model side definition of Q bar. This is the naive definition in terms of periods and the projective geometry of W check and D check. That's what all this stuff is. So if now we take an automorphic cohomology class defined over Q bar in the sense here, Penrose transform image, with pullback to W, okay, as a twisted relative de Rham class, and we let P be a CM point of W with image phi P. This is a Hajj structure of type 2-2 in the Siegel modular threefold. Then what one can say is that up to a transcendental factor, which depends only on the CM type of phi P, alpha tilde P, this lift back to the period side, is defined over Q bar as a section evaluated at a point of this relative de Rham bundle. Okay? So basically this is saying the notions of arithmeticity, there's a matching between the notions of arithmeticity, and really this is using classical stuff that was discovered by Shimura a long time ago, just applied in this framework. So another question you can ask is, what is the relationship of the first thing, which was canonical model, to if I'm in the non-classical setting, I look at a variation of Hajj structure into the period domain quotient or the Mumford-Tate domain quotient, and I pull back these automorphic cohomology classes and say, furthermore, my variation of Hajj structure was motivated over Q bar. So I had a family of algebraic varieties defined over Q bar, and that gave a period map. Then if I pull back, then what I'm going to get is I'm going to get a section of some Hodge bundles on S, right? Or some cohomology classes, some characteristic classes of Hodge bundles over S. And those Hodge bundles are defined over Q bar. And so you can ask whether there's any reason that should be actually also defined over Q bar. In other words, the pullbacks of those classes, if they're defined over Q bar in this sense, say. So that would be an interesting problem. Okay, now let me say something about cup products, but I'll have to do the short form. I'm not going to do any proof. Okay, so this says right up front what the result is. And the interesting point is that on each right-hand side, the cohomology here corresponds to a TD-LDS. So the TD-LDS... Yeah, okay. Right. Okay, so this says this really should be switched because you can see much more easily on this one. So what this is saying is that for G equals SL2 and K greater than or equal to 0, you have virtual surjectivity, I'll come to what that means in a second, of H naught of H mod gamma tensor H1 of H mod gamma with coefficients in L minus K and LK minus 1 onto H1 of H mod gamma with coefficients in sections of theta characteristic. Then for G equals SU21 and K greater than or equal to 5, or G equals SP4 and K greater than or equal to 5, you have these tensor products of H1s, both of which are Penrose transforms of classical things, or H1 and H2, the same statement applies. And those are combining into H2 and H3 of automorphic cohomology of L of something really small, L minus alpha. These are both L minus rows. And virtually surjective means that for each gamma, there exists a gamma naught in gamma, such that the composition of theta gamma naught with the push forward from gamma naught to gamma is surjective. And I'm not going to get into the other stuff because I'm not going to cover the proof. But I want to give the interpretations quickly. For SU21, that's the first one. For the left-hand terms of Carayol's result, you have that they're Penrose transforms of the Picard modular forms, or anti-holomorphic Picard modular forms. For the right-hand side, this is the interesting part. H2 of D mod gamma with coefficients in O of L minus rho, you have H2 of homomorphisms, torus invariant homomorphisms from wedge dot of n into the automorphic forms tensor C minus rho. Now the point is, the thing that you're going to use here, the thing that's going to come in there, the only relevant differential, is of this form, and it already has weight minus alpha 1. So you have weight minus alpha 1, weight minus alpha 1, so this guy has to have weight 0. And so we have something that has weight 0, and so it's going to descend to d modulo gamma. That's the first observation. The second observation is that F belongs to the lowest K type of a copy of the TD-LDS when you compute that. And that uses Castleman-Osborne to show that you have to have infinitesimal character 0, and the fact that the TD-LDS for SU21 is the only unitary representation with chi 0 and contributing to H2. And so finally you arrive that these are C infinity functions on d modulo gamma, which are Casimir eigenfunctions. And I've just normalized the Casimir so that I have eigenvalue 1. I'm not making any statement there. It's a particular eigenvalue. And altogether, the result states that you can combine Picard modular forms and get these Moss forms for SU21. All right. For SL2, what is this saying? Because it's a little bit interesting, and it sets up the case for SP4. To make this concrete, you can use the standard cup product on modular forms, essentially. I'm just using duality under that to map g of t to g of t bar, g of tau bar, y to the k minus 1, y is the imaginary part of tau, d tau bar. So what does this do? This sends you from modular forms of weight k plus 1 to C infinity modular 0, 1 forms of weight 1 minus k, modulo del bar operator. And this indeed has holomorphic automorphy, if you will. So that means I'm taking f and g, weights k and k plus 1 modular forms, and combining them into fg bar y to the k minus 1 d tau. And then I'm saying that up to del bar coboundary, this is, using the same correspondence again for these sections of the theta characteristic, these modular forms of weight 1, I can send f to f bar over y d tau. And so I'm saying that up to del bar coboundary, these are the same. So if I have any sections here, then they're going to be obtainable by taking tensor products of this form for sufficiently small gamma and for any k, which is kind of surprising.
Gamma means you pass to a subgroup of
You have to pass to a gamma naught to get, this is virtual surjectivity in that sense. So it's not necessarily, you have to go up in a tower and come back down. So then finally for SP4, I'm not going to sketch the proof, not in this talk at least. And what are these two things? They are Siegel-modular forms of weight k and Siegel-modular two-vector valued forms. And the weights here, you can see that they add to minus rho. And the issue is, again, the interpretation of the right-hand side that we're getting at by these cut products. So it turns out that this is isomorphic to H3 of, the N cohomology of one of the TD-LDSs for SP4. And reasoning as for SU21, you can deduce that these are functions on SP4R modulo gamma that are in the kernel of this differential operator, are Casimir eigenfunctions for this particular eigenvalue, which I've normalized so it's 1, and then F transforms with weight minus alpha 1 under the right action of k. So I said it's some weird non-classical analog of theta characteristics. But that's what one is getting at. And I mean, the proof does some nice calculations, but I'm not going to do it. Do I have a couple more minutes? I'd like to show something about the boundary components as well. So there's something called cuspidal automorphic cohomology. When you get to this point in the computation of the coherent cohomology, if you simply replace this by what you know the decomposition of, namely the cuspidal automorphic forms, then you recover a nice result. And then the problem is of interpretation. I won't worry about the interpretation, but what I'll say is you do recover the result about special values at CM points. This thing down here, you recover injectivity of the map. Well, you get that this map is injective. There's a natural map from SP into HP, from cuspidal automorphic cohomology to ordinary automorphic cohomology. That's injective for a lot of cases that we looked at. And the Penrose gives an isomorphism between cusp forms and the image of cuspidal automorphic cohomology. So that's another nice thing that's true. So
I guess I'm a bit perplexed. Gamma was compact. Well, now you talk about gamma as a
gamma is not, so I said let it be not necessarily co-compact anymore.
the heading of the section. I'm sorry.
Okay. Okay. I'm going to put up maybe.
This you want to do in order to make Fourier expansion?
That's right. So the idea is that you want, let me just put up this slide on what Carayol did. You can define using limit mixed Hodge structures some boundary components. And it turns out for the non-classical domain for SU21, that the boundary component he looks at is a CM elliptic curve. This is a beautiful fact. So what he does is he maps an automorphic cohomology class, or restricts it to a neighborhood of this boundary component. And then, by just a push-pull, he turns it into a sum of sections of tensor powers of some line bundle over this elliptic curve and gets Fourier coefficients in that way. And he proves that if you take as your notion of arithmeticity, the omega k's are defined over q bar, then he proved that the cuspidal automorphic cohomology S1, in different notation, is spanned by arithmetic classes in this sense for particular mu's. Okay? And so what I did with Greg Perlstein is I did a theorem, which I'm not going to put up because it's just a lot of notation. But what it says is that there's a correspondence between boundary components of Mumford-Tate domains and nilpotent cones in the Lie algebra, in the Mumford-Tate Lie algebra. And there is a condition purely on the level of the Lie algebra for the corresponding boundary component to a particular nilpotent cone to be a CM abelian variety. And so that would hopefully allow you to do some of the same things he did here. The importance of the CM abelian varieties is that while d mod gamma may not be defined over q bar, the CM abelian variety is going to be defined over q bar. And so you can use the fact that that guy has a canonical model to at least inject some notion of your Fourier coefficients being defined, being arithmetic, even though you can't say that your class is defined over Q-bar. So you can define Q-barness for your class that way, maybe even for G2 Mumford-Tate domains. So anyhow, thank you very much for your attention.